Hi! I did a quick unboxing video of this UNI-T UTG1042X arbitrary waveform generator in the last episode, and today we're going to do a detailed review. The UTG1042X offers a 16-bit vertical resolution and a 200 megasamples per second sampling rate, with a maximum output frequency up to 40 MHz. Functionality-wise, the UTG1042X is very similar to that of the UTG1042E that I reviewed a couple years ago. In fact, as you have seen in the previous video, the user interface of the UTG1042X is virtually identical compared to the UTG1042E. So as you can see here, this screen is virtually identical, and the layout is also pretty much identical here. And as a benefit of this, if you are familiar with one of the waveform generators, you will be able to use the other one without the need to refer to the user manual. Now at around $350, the UTG1042X cost almost twice as much as the UTG1042E. So naturally you may ask, what are some of the obvious benefits that warrants this increased price tag? Putting the obvious form factors aside, I think there are a few advantages UTG1042X has over the UTG1042E. The first one is the vertical resolution. The UTG1042X has 16 bits, whereas the 1042E has 14 bits. Now, for the majority of applications, the difference between 14 bits and 16 bits are not as significant as you might think. In fact, for the majority of the use cases, I would argue that 14 bits vertical resolution is probably going to be sufficient, unless your application is sensitive to quantization errors. One of the trivial examples is when you are using the waveform generator to output a DC voltage. With 16 bits, you will have less offset error because you have 2 more bits to play with. Another potential benefit is when generating sinusoidal waveforms. In theory, the higher the vertical resolution, the higher the fidelity of the generated quantized waveform, and in theory that translates into better spectrum purity. Now, I said in theory because there are other factors, such as filtering implementation and the phase noise of the DDS. They also play a crucial role. One area where the 1042X really shines is its arbitrary waveform capability. The 1042E does have some built-in arbitrary waveforms, but the user-defined arbitrary waveforms cannot be persisted, which is very unfortunate. But for the 1042X, not only it has a ton of built-in arbitrary waveforms. According to the specifications, there are 200 of them versus the 24 built-in ones in the 1042E. It also supports user-defined arbitrary waveforms, each with 2,000 points, which we'll take a look a little bit later in this review. So the arbitrary waveform capability of this UTG1042X is a big selling point, in my opinion. Besides the arbitrary waveform capability, the 1042X also added more modulation options. For example, besides FSK, it now supports ASK, PSK, and PWM, and it added burst function in the modulation options as well. Alright, with the overview aside, let's actually take a closer look. What would be better to use just review the UPO1204 to monitor the output from the UTG1042X. And currently we're just outputting a sinusoidal, is at 10 MHz, and you can see how easy it is to use this UTG1042X. I can, for example, come here and change the frequency here. So for instance, it's frequency and period. So of course I can use the arrow keys to fine-tune which digit I'm trying to adjust. So let's just say we wanted to go all the way down to 1 MHz, and also let's say we want to change the unit to kilohertz instead of megahertz, and I can do that. So let's require the signal here. And of course you can adjust the amplitude and offset. For example, if you want to adjust the amplitude, you just come down here. The arrow keys work the same way here, so let's adjust, let's say, to 300 millivolts, and you can see that is adjusted no problem. And of course we can adjust offset and everything else as well. Now the 1042X compared to the 1042E added another manual function that we didn't find on the 1042E. You can see we have a return. This is very useful. On the 1042E, for example, you see here, once you adjusted this, there's no way for you to go back, but you have to press the waveform itself. So that's how you get back to the previous manual, whereas here you can just press return and you will go back to the previous manual. Of course, here we have different waveforms for you to select from, and it's very intuitive. So let's go to the square, and you can see that's a square wave on the screen here. While we're measuring the square wave, let's actually take a look at its slew rate. So for that, I think I'm going to change the amplitude to 1 volt, so it's easier for us to see, and it's a round number. So let's go to amplitude. And by the way, we have a different way to enter data. Instead of using the rotary encoder, you can also just punch in the data yourself. So for example, 1 volt, and it's very convenient. And of course, let's require the signal. So let's actually expand the horizontal scale a little bit so that we can see the waveform a little bit more clearly. This is our slew rate. And you can see right now we're at 25 nanoseconds per division. And this is definitely not the steepest that I have seen. And if I remember on the 962E, the slew rate is independent of the frequency. So let's actually verify that here. So let's go to frequency and let's increase it to 10 kilohertz. Yep, you can see it's not changing. And let's do 100 kilohertz. Still the same. Let's do 1 megahertz. Doesn't seem like the frequency is impacting the slew rate here. So the slew rate essentially is fixed. So now we're at the 10 megahertz. You can barely recognize the square wave anymore. And just for curiosity, let me swap in the signal output from the 962E, and now I have adjusted it to output the same 10 megahertz 1 volt peak-to-peak signal. So let's take a look at the slew rate. So actually, let's just concentrate on the rising edge here. So let's see here, it's roughly 2 divisions. And let's swap in that signal here. And you can see that we have pretty much the same slew rate. Of course, there's a little bit of a difference in the frequency response, but that is irrelevant in this measurement. And now we're looking at a 1 kilohertz pulse signal. For the pulse signal, we can actually change a couple more parameters. And let's actually take a look at the duty cycle here. So I can go down here and let's change the duty cycle to say, oh, the shortest is actually 0.002%. That's actually quite nice. Let's see if we can get it any lower. Nope, 0.002, that is the pulse. So you can barely see that here. Let me expand the horizontal a little bit. So that actually is a fairly short pulse here. So that's actually going to be very useful. And of course, we can increase it all the way up to, let's see what is the highest, 99%. By the look of it, we can also go up to 99.998. So essentially, it's the inverted pulse of what we had before. So let me adjust it to say 50%. Well, let's do 10%. 10%. And let's actually change the slew rate here. So let's see, the rise time right now is set to 15 nanoseconds. And let's come down here. Rise time. Let's see if we can get it any lower here. Nope, it looks like the 15 nanoseconds is the lowest, but we can increase it. So let's see, we wanted to increase it to 25 nanoseconds. Yep, you can see the slope changed here. So it seems like the rise time limit is 15 nanoseconds, and that is the same as what we have observed with the square waveform. And this is independent of the frequency. So let's take a look at here. So let's go back to frequency, and you can see we can change the frequency, and the rise time does not change. And here is a ramp signal. You can see that we can also change the symmetry of the signal. And of course, we can add modulation on top of the signal here. Right now I have a 1 megahertz signal, and let's add some modulation. And let's do modulation AM. Okay, so I think I need to change the scale a little bit. Yep. And you can see that we have this amplitude modulated signal. Not a problem. So let's change the modulation depth to say 50%. And you can see that we also capture that signal. Now, of course, it's not as stable, but the signal is captured nevertheless. That's our AM signal at 50% of modulation. And you can over-modulate the signal, so that shows you an over-modulated AM signal. Here you're looking at a frequency modulated signal. The carrier frequency is 3 kilohertz, and the modulation is 100 hertz with a frequency deviation of 1 kilohertz. Then let's change it to phase modulated signal here. So I come back here, modulation. Let's do phase modulation. And you can see that phase modulation is similar to frequency modulation, at least from the waveform you can see here. Right now we are using the same carrier waveform at 3 kHz, and the modulation frequency is 100 Hz with a phase deviation of 180 degrees. Let's go back here. And let's take a look at the amplitude shift keying here. And remember, on the 962E, we only have the frequency shift keying. We don't have this amplitude shift keying. So let's actually do this to see what we got here. So you can see we essentially have two amplitudes, one for 1 and one for 0. And that is the behavior of the amplitude shift keying. And you notice that right now the modulation source is internal. Of course, we can change it to external, but right now I don't have an external source. And if you are using an external source, you would put it in this BNC here. And this can be quite useful when you are testing, let's say, an equipment like radio or something like that. So let's go back. And let's take a look at another modulation here. Let's do frequency shift keying. And here is a captured waveform of a frequency keying signal. And you can see as we're hopping between 10 kHz and 2 kHz with a hop rate of 100 Hz. And this is a waveform of a phase shift keying signal. And you can see the abrupt phase shift here. So let's actually change the phase to something else here. And you can see the difference here. So for example, we're doing right now is 0 degree. Let's start with that. And that's a continuous signal. And let's do 10 degrees. You can see here we go to 90 degrees, and what we saw before was 180, and let's do 270, and then 360. That goes back to 0. And here is a pulse width modulated signal. I slowed down the modulation rate to 1 Hz so you can see it clearly on the oscilloscope. And what you're looking at right now is we're doing a sweep between 10 kHz and 100 kHz with a sweep time of 1 second. And here is a demonstration of the burst mode. You can see we are currently outputting 2 cycles, and we can change that to 3, 4, so on and so forth, and back to 1. Next, let's take a look at some of the built-in arbitrary waveforms, as after all, that is one of the key selling points of the 1042X. So let's go back here. Let's go to arbitrary waveform. Now, the way it is actually structured is a little bit confusing here. And you can see here, to select the actual arbitrary waveform, you have to go to the wave file. And currently we have local and user. Now, the local is what is stored on the device. User is what you can put in later on. I'll show you that. But let's actually go to the local here. So let's press, and you can see we have a lot to select from. Each one of these is folders, but we have essentially 12 categories of all the different waveforms. So let's actually take a look at one of them, the interesting one. Let's do the bioelectric one. And let's come here. You can see we have the EEG and so on and so forth, all these different waveforms here. And of course, we can go back and let's select a automotive. And you can see we have quite a few of these different waveforms. And as I mentioned in the overview, you can also design your own arbitrary waveforms with the 1042X. The software UNI-T provided for communicating with the PC did not change that much between the 962E and the 1042X, so I'm not going to go into details in this video on how to use the software and how it works. If you are interested, you can check out my 962E review video, as I did a thorough walkthrough of the software and the process there. The software is a little bit unpolished, I have to say, but it does get the job done. Once you have saved your arbitrary waveform file, you can upload it to the 1042X in a couple ways. One way is to load it through the computer while the device is connected, or you could save the BSV file to a thumb drive and connect to the front USB port here on the 1042X. So let me demonstrate the latter here. Now I have designed a arbitrary waveform earlier, and I have put it onto the USB drive here, so let me plug it in. And once you plug in, you see the icon here that indicates that the USB file is recognized. So let's go back to the WAV file here. And you can see now, besides local user, we have this external. So let's go to external. Let's go to external, and here you can see that we have this wave data.bsv. That is our saved arbitrary waveform. So let's hit OK. And now you can see we are displaying the arbitrary waveform on the oscilloscope here. And let's go back here. Let's just take another look. Alternatively, you could also come to the utility here, and you will see Arbitrary Waveform Manager. And Arbitrary Waveform Manager, you can see here, we can also use that to get to the actual waveform here. Now, here we have an option to import the waveform into the onboard memory here. So, for example, if I do import all, of course, we only have this one arbitrary waveform currently, but I have imported it, and let's return here. So let's take a look. And you can see we have the arbitrary waveform data. So just to make sure that this is actually saved on the device, let me unplug it and let me power it off. And I'll re-power it on. So let's go to arbitrary waveform and waveform file. Let's do user. And you can see that this is actually saved onto the device. And the reason the waveform looks a little bit odd is because right now the frequency is too high at 10 MHz. So let's actually lower it a little bit. You will see that the waveform will become a little bit more crisp. So let's go down here. Let's do 1 kilohertz, and you will see. And that is our waveform. You can see that there's no problem at all. And remember, because we have a 16-bit arbitrary waveform generator, I do expect the output voltage setting to be a little bit more accurate on this one compared to the 962E. So let's actually take a look. So let's go back to waveform. Let's go down, and let's output DC. So let's actually measure the output voltage using a multimeter. So I'm putting in a BNC to alligator clips. And I'm going to use my UNI-T UTG1042X Plus to do the measurement here. So all the equipments here are UNI-T. So now we're outputting 0 millivolt. Actually, let's change it to DC here. That would help. So we do have a little bit offset, which is at 0.19. And I don't remember what it was like with the UNI-T 962E. So let's actually take a look here. So now I have the 962E here. You can see that it's outputting 0 volts. So let me connect that to the 962E instead. Yeah, as you can see, the offset is actually a lot higher. Right now it's at 0.3 volts. So let's go back to the 1042X. And let's change it to 1 millivolt. Let's do 10. You can see we do have some offset, but for a function generator, this is actually pretty good. So let's do 100 millivolts. 1 volt. And of course, let's come back here. And I have to say that is pretty good for 1 volt. Alright, let me demonstrate a few more features of this UTG1042X. And one feature it has is the frequency counter capability here. So for that, let's go to Utility and Frequency Counter. You can see right now I'm actually inputting a signal from my UTG 962E. You can see that's a 10 MHz signal, and we're counting this correctly here, roughly 9.999. And by the way, there is some limitation to the frequency counter here. The input signal has to be TTL compatible. Just wanted to point out. Yeah, let me vary the input frequency, and you can see that. Let's do 9 megahertz. And you can see that we pick up the frequency with no problem. And as I pointed out, if it's not a TTL signal, unfortunately, you will not be able to capture the frequency here. So let me demonstrate that. For instance, right now I'm at, you can see here, the amplitude is 5 volts. And let's actually drop that. Let's change the offset to 0 here. And let's change the frequency down to say, the amplitude down, say 1 volt. And you can see actually we're not picking up any readings anymore. So that's one of the limitations you need to pay attention to of this UTG1042X. And another feature I wanted to point out is this UTG1042X, you can actually change the output impedance. Currently we're at high Z, that's high impedance. So what it's doing actually is not really changing the output impedance. It is just merely change the output voltage to match that impedance. If the load, for example, is 50 ohms versus 75 ohms versus high Z, the output voltage would change. So let me actually show you that. For instance, right now we're at high Z, and I actually changed the output to just 10 millivolts so we don't interfere with the measurement here. So if you can see, we're doing the ohm measurement on the output here. So let's do that. You will see that the actual output impedance is roughly 50 ohms. So right now we're at high Z, and let's actually change that to say 50 or 75 ohms. And you can see now we're showing 75 ohms, but the output is still at 50 ohms. So basically the output is always 50 ohms, but the software adjusts its output so the displayed voltage matches the intended load. Next, I wanted to take a look at the spectral purity of the 1042X and compare that with the UTG962E. As we mentioned earlier, this one has a 16-bit output DAC, so in theory the output should be cleaner compared to that of the UTG962E, which only has a 14-bit DAC. Now the difference would probably be very minute, but let's take a look if you can spot that. And what's humming in the background is my HP8566B spectral analyzer, and currently we're outputting a 10 MHz signal with an amplitude of 100 millivolts RMS, and the actual amplitude doesn't really matter. I just wanted to be consistent with what we're comparing with the 962E. Anyway, so let's take a look at the spectral analyzer here. So currently, the spectral analyzer is sweeping between 5 MHz and 50 MHz. And you can see we have a very clean tone with very few harmonics around the base signal. And we need to remember that as we'll compare to the signal from the 962E. So now let me actually swap out the output from the 1042X to 962E. And you can see that the signal actually is fairly comparable, but we did see a little bit more harmonics next to the 10 MHz signal, which is our main tone output. Potentially that was the difference between a 14-bit DAC and a 16-bit DAC. Now, of course, there's a lot of implementation details could contribute to these differences that you see. Alright, I think that's all I wanted to cover in this video, and I will save the teardown till the next time. I hope you enjoyed this review, and if you liked the video, please remember to give it a big thumbs up and don't forget to subscribe to the channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will catch up with you next time.